Yes. So we are going to share the experience on enhancing the unconventional oil and gas recovery for the depleting wells by using the biotechnology. And we are also cover some other application in the conventional when I'm introducing, if you are working in the unconventional, uh, exactly this is what we are trying to introduce into you. But if you are working on the conventional oil field, similar concept can be leveraged to the conventional also. So we are going to have some other application in the conventional part. The mission of our company is to unlock the reservoir value with the advanced subsurface microbial technology. I remember when I was at the University of Oklahoma, we have a lot of courses on the on petroleum, on petrophases, and the chemical or the physics or the water testing, but we never had one class to talk about the petroleum microbiology. But as you know, the oil was converted from the organic to crude oil hundreds of millions years ago by the bacteria, and after bacteria used up the nutrients, then they decided to sleep in the formation. So now we are trying to get back to the formation and to wake up the bacteria live in the reservoir for 100 millions of years, so that it may help us to achieve the goal, double the EOR for unconventional shale oil, and increasing the oil recovery rate by at least 12% or more. Our vision is that tomorrow's oil is from yesterday's wells. We are going to have a limited drilling inventory. So how can we get the mm, recover more oil from the existing oil field, more economy, and also more environmental friendly? That is going to be the challenge facing in front of us. We are not a new company. This company has about 20 years of history. Auto Recovery was founded based on the acquiring the intellectual property from Glory Energy in 2017. Glory Energy was a public company specializing in enhancing oil recovery by using the biotechnology, but it only focuses on the conventional. We are leveraging the experience from conventional to unconventional biotechnology. based on based on my starting experience at the OU. When I was studying at the OU, my major focus on the enhancing the production rate by using hydraulic fracturing or refracturing, or by screening the fraction candidate by inventing some index like a fractility index. But I found that even after I have been trying the best to work on optimizing hydraulic fracturing or hydraulic fracturing fluid, or optimizing the design for refracturing, I still found that we cannot break the records of to reach 10% the recovery factor for unconventional. So I think there might be something we forgot in history. So then, when combining both biotechnology and the knowledge in understanding about the production behavior in unconventional, I think we come up some solution for unblock the value of unconventional. So in history, we have a lot of we- a lot of records and get the awards from the Energy Institute and the World Oil. One thing I might need to mention that our company had the USDOE $149 million loan underwriting phase approval from the U.S. Department of Energy, and we are applying this low interest loan to the K County in Oklahoma, that near Tulsa, with a company called Purdue Petroleum. They are working on the CO2 flooding in that area, but there are some shallow area cannot be used for cannot using CO2 flooding for enhancing recovery, and we are putting the including the biotechnology into the water flooding process. And in the meantime, for CO2 flooding, like you do CO2 flooding for 1 week or 2 weeks or 1 month, then you followed by that you do the water flooding. We are going to include that into the stage of water flooding so that you can have a better sweeping efficiency, so that you can sweep the unswept oil and increasing the efficiency of CO2 flooding. Uh, we have a lot of historical projects and ongoing projects all over the world. The major part is in the US and Canada, and we also have some ongoing projects in China and in the Middle East, and we also have some did project in Brazil. So currently, we are mainly focused on the US market that can see the COVID-19. We have a lab in Houston to support the microbiological screening and the chemistry analysis for the sample we collected from the field. We can do both aerobic or anaerobic cultivation of the bacteria. Aerobic means we are going to inject in the low concentration uh, of air to the formation. It's not going to cause corrosion. Anaerobic means zero oxygen in the injection water. Both technology has the advantage and the disadvantage, but it should fit for the right oil field. And we have the equipment to support the field operation. So in summary, we are trying to using the biotechnology to addressing the six area subject in the oil field. Number one, to optimizing the water flooding so that we can sweep the unswept oil and reducing the water cutter. The second thing is the ultra-shale, that for enhancing the unconventional oil recovery. Mm, if you believe that you have formation damage caused by the fraction fluid or high viscous gel, something for the unconventional gas, it might work also. And for paraffin cleaning and addressing the H2S mitigation, in, instead of using biocide, we're making it using this kind of biocompetition to kill the surface reducing bacteria and control the corrosion caused by the bacteria. Um, as you know, for the breaker, mm, to break the cross-link gel or some, the highest efficiency breaker can break only less than 40% of the gel, but we are trying to using the bio approach to training the bacteria to eating the gel so that you are going to have a less damage caused by the fraction fluid during hydraulic fracturing. So these are kind of additives. So subsurface microbiology is a big topic. What are the challenges in the unconventional resource for both gas and oil? Number one is the extreme low EUR. If based on oil price like $50, most of the $50 per barrel, based on the current recovery factor, most of the oil company can only meet the ends. So, but they need to make profit for the investor and for the owners. So if we can double the EUR, I believe most of the shale gas and shale oil field, even at the oil price like $50 per barrel, it is still profitable. The second thing is the rapid decline curve. After about producing for about 9 months to 12 months, the production rate for the completed horizontal well decreased by about 70%. So currently facing the pressure of capex. Instead of drilling the new well, we may go back to the older well if we can uplift the production decline curve and get the production back, increasing the, for example, increasing the production rate by about 100 barrel per day, that is going to be a significant progress. And for the recompression, if we are doing the refracting or something, that's still a game like a few $1 million. But when we are talking about the increase in the EOR by about a 5% or 10, recovery factor by about 5% or 10%, that is the cost not $1 million. That is a cost about a few like a $100,000 only. It's not $1 million game, and it's affordable by most of the operator. If you look at the production decline curve in the Permian Basin, we take this is the public data from a public company. You can see that the average daily oil production rate, the first 6 months, the second, the third, the fourth 6 months, that means the production decline very fast. So when we are screening the candidate, we are looking at the horizontal well, the area with very high IP30 or IP60 or IP180, then the production decline. That means that there are significant production decline. That means there might be some damage or some pollution to the fracture network. So we're thinking about we need to go back to those wells with very high initial production. That means that by nature, they are born with very high production. Then how can, but they were affected by the pro, by the production rate. Excuse me, can I just hold on for 1 second? Because I have a urgent call from the family. Just 1 second.
Yeah, 1 second. Yeah.
They keep on calling me. Okay, we can continue.
Thank you.
From the hospital, it asked me to pick up some medicine. Thank you. So we are trying to recover, to uplift the decline curve, so that if the well has been producing for about 3 years or 4 years, or some of them producing for about 9 years, how can we go back to these kind of depleted wells and enhancing the production back to the to 10% or 30% of the initial production? That is the that is the objective. I believe we can achieve some of the goal. So how to stimulate the indigenous bacteria? We must claim that we are not injecting any external bacteria to the reservoir. We are trying to wake up the pre-existing bacteria already in the reservoir or in the fraction network. They have been existing there for 100 million years, but they are not active because they miss the nutrients. They used up the nutrients in history when they converted the organic to the oil. But now we are feeding them back with the nutrients like vitamin, and then they can grow. As for the carbon source, for any bacteria, they grow in carbon, but they have enough carbon source from the fraction fluid, the chemicals like gel, emulsion, oil and water emulsion, or HPAN, or or the fatty acid in the crude oil. So there is this is the growth triangle for the individual bacteria stimulation. We are going to mix in the nutrients in the water, and then they can go to the fraction network. Then they grow. When they grow, then what is going to happen? You can look at the in if you're in the compression engineer, you will be very familiar with the composition of the fraction fluid. There is friction reducer, there is some gelling agent, and they are cross-linked. So all these things, they're going to cause potential uh, damage to the fracture network. We do hydraulic fracturing because the formation permeability is very low in the mini dash. We believe slick water is a very success, yes, but not many people critical thinking like that way. Is this kind of a low EUR partially caused by the slick water? So slick water contributing to the success of shale gas. I think slick water also attributing to the low EUR for the shale gas and the shale oil. Why? Although the dosage is less than like 0.5% is very low, but we are addressing the formation in the nanometer in the nano dash. So they are going to be absorbed to the fracture surface and block the pores in the nanometer, especially the friction reducer was linear if they are in the fresh water, but in the formation you have the calcium ions and you have the irons, and then they are going to aggregate. When they aggregate, the size increase, and the shell formation has a higher content uh, of clay, and the clay the clay had the highest surface, the ratio of surface area to the volume. So these kind of aggregates, they're going to be very easy to be absorbed to the fracture surface. Even though we have the fracture channel, but the hydrocarbon flow from the matrix through the fracture surface to the fracture and then to the borehole, then that means that there is a door between the matrix to the fracture channels was blocked. So we cannot, even by using the breaker, the for it cannot break all of the all of the gels. And for the friction reducer, the polyacrylate, it's impossible to break them. They're going to be in the formation. Even for the gel, you can only break like 30%, 40%. Then that they're going to be left in the formation forever. The other factor we are going to mention that is, I'm going to talk about that in one more page. So we did some tests in the lab to show how the how the friction reducer absorb to the shell cutting surface. You can look at by using the NMR, uh, showing the picture after 20 minutes. The red representing the pores, the blue representing the etchpan. In the first 20 minutes, we can see that there are still some pores on the cuttings. But after 60 minutes, you can see that red pores are decreasing. After 150 minutes, then most of the red pores disappear. It was covered by using the etchpan. That means that the etchpan has significant uh, damage to the shell formation. So we need to think about how can we clean them, how can we permanently to clean them so that this kind of permanent permeability loss can be recovered by some approach. The other fact, uh, most of the industry um, forgot is the water in oil emulsion. For this part, when we are making the friction reducer, usually you have the petroleum distillate or some diesel, so that you can emulsion, you can have the friction reducer to reducing the pressure loss. But that kind of oil and surfactant added during the hydraulic fracturing is going to form in the oil in water emulsion. This kind of emulsion particle size about 0.02 micron to 2 micron. They are going to block the micro fracture permanently. So this might cause the results of low flowback and the low EUR. So in summary, one thing is the water in oil emulsion. The other fact is the gel used during hydraulic fracturing and the friction reducer. The three factors contributing to the loss of fraction network conductivity. So we are going to go back to addressing this problem by growing the bacteria. Yeah, this is the another thing we might mention is the consider the environmental side. The industry is reusing the water for hydraulic fracturing and for the recycled water, the salinity is very high and it contains the ions like calcium, magnesium, and the iron. So it's going to cost the, the aggregate of the friction reducer. So our approach can be a kind of additive to the recycled water so that we can continue using the recycled water, but not causing the formation damage. In the lab, we did the test on the fraction fluid like guar. Uh, for example, before the test, there the guar look like this way, but after the test, is they break the it shows the bacteria growth. This color representing the growth of bacteria. After about 10 days, more bacteria grow, and then we tested the viscosity for the guar, and the viscosity decreased by more than 90%. That means most guar has been degraded. For the HPAN, similarly, we show that the bacteria can grow when the HPAN existing in the liquid. After about 10 days, it shows a lot of HPAN grow, but we cannot test the degrading of HPAN by by testing the viscosity change because the viscosity of HPAN is very low. But instead of doing that, we have some other approach to test that. For example, in the lab, we're using the HPAN we collect from the third-party service company and using the produced water from the Permian Basin to grow the bacteria with the existence of HPAN. You can see day 3, the geometry of the HPAN like this way because the bacteria grow on the HPAN structure. Day 6 it go this way, day 9 it grow like this way, day 12. That means after about 10 days, the bacteria break they break the HPAN from the long chain to the small chain, so that then they can from the big molecule to the small molecules. Then they are not going to block the nanopores, and they can to some extent they can clean some of the fracture surface. And also we're using the the UVs to test how the UVs means if the chemical was degraded, then more light can get through. We test that on the HPAN, on the Janssen, and also on GUA. Uh, the control group has lower uh, the UVs percentage, and then for the group with the nutrients, it has more light pass through the sample, and then that means most of the chemicals has been degraded by using the UV rays to test for the GUA and also for the ginseng and for the HPAM. So we are going to go to the field and to prove the concept that we identify in the lab. So the procedure we're going to do analyzing the production data and the calibration data provided by the operator to see whether there are some potential damage to the fracture well or not. And then we collected the produced water and the oil from the wellhead, and we verify whether our formula can degrading the chemicals in the fraction fluid by using your water or not. And then we go to the field to do the Huff-n-Puff and shut in the well for about 5 to 10 days, and then resume production. Then we are going to check the EOR for the well. Here I'm going to show one pilot, two pilots we did in Delaware Basin and the Midland Basin. Uh, Both of them are in the Wolfgang A. The first well this is the horizontal well. I think yeah, this is horizontal well we did in the Delaware Basin. Before the treatment, the daily liquid production is only 160 barrel per day, and this horizontal well completed in 2014, and we did the pilot in 2018, if I remember. No, in 2009, in 2018 in July, and then we only inject the 500 barrel because this is a pilot well. So we are trying to limit the injection volume to avoid the pressure build up, and we limited the number of days of shut in to minimize the pressure build up so that we can better interpret the result. We only shut in 7 days. So so then after we resume production, you can see that the daily liquid production increasing from 160 barrel per day to 300 barrel per day up by the September. So 30 days after that is increasing by 40%, 60 days, 82%, and 90 days compared to pre-treatment, 95%. And then the if we look at the oil production, it increasing from about 80 barrel per day to 100 barrel per day. Then it's going like this new decline curve. This only for 6 months, but we have the data for 18 months. If you look at the decline curve, if we do not do any treatment, it's going to decline this way. But by after the treatment, it goes with a new decline curve. That the 18 the EUR incremental is 18,000 barrel. So for this case, we only treat 500 barrel. We believe most of the injection liquid only go to the hair of the horizontal well. For now, for the industry, for the real scale, we are going to scale up from 500 barrel to 5,000 barrel injection. So that is significant, and we are also doing that for some operator in the Permian Basin, but the data is kept confidential. We cannot disclose here, but we get very promising results. The other pilot is for the very marginal wells. Is vertical well, fractured by 4 stage. It completed in 2014, and the pilot was also done in July 2018. The daily production is only 2 or 3 barrel per day. It otherwise to be abandoned. Like you call that as marginal wells. The monthly daily liquid production is only 500 barrel per month. So we also inject a 500 barrel nutrient liquid to the formation. So after 30 days, the liquid increased by 127%, 60 days, 70, 90 days, 70. And then we look at the oil production increase. The oil production increasing from 3 barrel to about 8 barrel per day. And if you look at the decline curve for 18 months, this one is the old decline curve before the treatment. Then after the treatment, it goes with a new decline curve. So the incremental EOR is 2,200 barrel. Why it go like this way? As I mentioned that the cleaning of the fracture in the formation is a forever cleaning. It's a one-time treatment, then forever cleaning the channel, because after you're degrading the fraction fluid that kept residue, then it's cleaning forever. Especially for this case, they are using cross-linker gel in the formation. I believe the nutrients stimulated the individual bacteria, and then the bacteria in degrading the gel, the cross-linker gel that cannot be degraded uh, by the traditional breaker. if you happen to have some wells you ever fracture with the breaker, no, with the cross-linked gel, I think this kind of biotechnology offer a better option for you to do the formation cleaning forever. So we may expanding that for another scenario for the hydraulic fracturing of the mother well and the child well, because in the Permian Basin, most of them are fracturing, when they are fracturing the mother well, the child well, they need to shut in the mother well. When we are shut in the mother well to avoid the that can the fracture goes to the mother well, the operator always brush up the mother well by injecting 5,000 barrel to 20,000 barrel water to the mother well, and so that and shut in the well for about 10 to 20 days. In that way, we are trying to encouraging the operator to make use of the time window to shut in the mother well, and by mixing the nutrients into the water, and then they can also not only just shut in the mother well for improving the hydraulic fraction, but also to do one one EOR job. The other option is if we believe that there is a formation damage in the fraction network by the fraction fluid chemicals, why don't we add the nutrients in the fraction fluid from the very beginning? Like we can mix in that like the nutrient, like the tracer, you know, during hydraulic fracturing, many companies are using tracer to monitor the flowback and also the production profile. So similar ways, we can mix in the nutrients at the same time during hydraulic fracturing by plugging that to the low pressure end of the fraction pump. By doing that way, before flowback, that the 2 week to 3 weeks time window is going to allow the nutrient to stimulate the bacteria, and then the bacteria is going to degrading the hydrofracturing chemicals that enable the operator to using relative higher viscous fraction fluid and achieve better proppant placement, and not worry about the potential for fraction network damage caused by the viscous fluid, because we have the bacteria to degrading that, and it's not going to affect any any operation. It's not going to increasing your it's not going to increasing your operational cost significantly. So regarding to the market projection, we did a research for the vertical well in the Permian Basin, horizontal well in the Permian Basin, Eagle Ford. So the potential EOR market is about $30 billion. I think we did the valuation based on the WTI price at $55 per barrel. When we compare the technology with other technology, like a gas Huff-n-Puff, our production downtime is only 2 weeks. The Huff-n-Puff for the gas is 3 months. It required operation pressure above the 5,000 psi, and we do not require the minimum pressure. And the target basin, we don't have a limit, but the gas Huff-n-Puff are mainly used in Eagle Ford. The EOR uplift the percent by using gas Huff-n-Puff is about 30%, also is about 10%, but the payout period is only 2 to 4 months, and the cost per well is $50 to $200. But that depends on how many stages or how many wells. If it scale up, the cost can go down. But for the gas Huff-n-Puff, the cost is at least $1 million or more. Another mathematical game is like compare with new world drilling or reef fracturing. The budget for the horizontal well drilling and completion for them is about $10 million. But if we have $10 million, we can do 100 horizontal well Huff-n-Puff by doing fracturing a new wells, you're going to get about 1,000 barrel oil per day for the flowing barrel. But then by spending $10 million on 100 horizontal well for EOR, you are going to get the 10,000 barrel oil per day. So the cost per flowing barrel is $10,000 per flowing barrel for fracturing. But then for the EOR, it's only $1,000 per flowing barrel, and it's going to increase in your reserve significantly. So the cost per flowing barrel for unconventional EOR is only 10% of less than 10% of drilling and completion. So it's time for a game change in developing the unconventional shale oil or gas in the downturn of the petroleum industry. Yeah, so I'm going to mention about the weakness of our technology, that we can only apply to the formation with a temperature lower than 96 at 190 Fahrenheit. The salinity is lower than 130,000 ppm. But based on our test, even though the salinity is about 200,000 ppm, it does not have the field result based on the recent discovery in the field. So this is a map showing that the temperature gradient in the U.S. Permian Basin is good. Some of the formation in Oklahoma also fit for the temperature requirement. The last thing, I'm going to go very fast for the conventional, especially in the scenario of water flooding. The conventional water flooding like this, but by using our new approach, is going to put a tank just at the wellhead or in your injection station, so that you're going to inject mixing the nutrients with the water to the formation, and then they are going to grow the bacteria in the formation and block the preferred water channel. We have pilots in Kansas and in California. In Canada, you can see that after a few months of the injection, the oil production increasing from about 60 barrel per day to about 110 barrel per day. It can show that it uplifted the production decline curve. And in California, it also can show that for this case, it shows the production increase. And in Canada, it shows that the production the continued injection for about 24 months, the production increasing from 30 barrel to 200 barrel per day, no, for about 100 barrel per day, sorry. And they're reducing the water oil ratio, so that it means the same amount of water injecting into the formation, you get more barrels of oil. It can also help to preventing the paraffin deposition, this kind of flow behavior. Usually do like this. We inject in the nutrients from the annulus and shut by using the water, a few hundred or a few thousand barrel. We shut in the water for about 5 to 10 days, and then resume the production. You're going to see the production increase. For example, for this well, before the treatment, they need to do the walk over every 2 months. But after doing the treatment, then the operator, you can see the blue line representing the oil production rate. After the treatment, the oil production increasing from about 5 to 8 barrel to about 60 barrel per day. So this we're doing very good, but we also have some other that does not have such good production. So if you believe that you have the near wellbore damage, or if you have the if you have the formation damage in the fracture network by the traditional completion approach, gel or GUA or the fission reducer, for the single well Huff-n-Puff, it can address in the near wellbore damage and also near fracture surface damage very efficiently. If you are facing the very high water cutter, like a 90% or 98% water cutter, there is preferred water channel in the formation, we can consider this kind of continuous injection of nutrients from the water, so that you can reducing the water cutter and the sweeping and the force diverted water sweeping the unswept oil. So thank you so much. I'm happy to answer some questions.
Thank you so much, Jacob. I know that a big thing that we're always hearing is, how do I keep my marginal well going? And, what can we do to make that lifetime go a little bit longer? So it's always nice to just hear about the technology or the processes that we can do.
Yeah. So this is mainly focused on extending the life of the marginal wells. Yes.
Yes.
Yeah, I'm happy to answer questions. Yeah.
Yeah, and if anyone has questions, please feel free to unmute yourself, put it in the chat, whatever you'd like. And if right now you're like, I just gotta, kind of take it all in, and if you come up with a question later, you can always email me. You can email Jacob. I know he's put his email right there. Or if you want the presentation, email me. But other than that, I'll give a minute. Does anyone else have any questions or anything like that? I mean, you did a really good job explaining all of it, to be honest.
Yeah.
Okay. Oh, where in Kansas is the I can never say this word, microbial water flood?
Yeah, that's what flooding. Yeah, that in Kansas. Yeah, I forgot the county name. Yeah, but we have the SPE paper published. Yeah.
Awesome. Okay. Well, other than that, guys, if you have any more questions, like I said, please feel free to email one of us. I'll make sure it gets to Jacob. Other than that, thank you guys for coming out today. And thank you Jacob, thank you for joining us and just educating us.
Yeah, the operator, and they asked the operator that the merit energy is the operator. Yeah.
Okay, there you go. Good catch. All right, guys, I'm going to go ahead and end this. Thank you guys all for coming out. Thank you, Jacob.
Okay, thank you. Thank you for your time. Yeah.
Have a great day.
You too.